Hello guys, welcome to this lecture on topology. I am Theophile Temaju, and before we start, please don't forget to subscribe to my YouTube channel. We are going to learn more about mathematics. As recall, in my second lecture, I defined a topology on a set, and we saw that if X is a set, then a topology T on X is a subset of the power set of X that fulfills, that satisfies the following nice properties. We saw also that if you think of a set together with a choice of a topology T on X, then you think of this couple, of this pair, XT, called a topological space. Also, a subset U of X that happens to belong to T, to some topological space, is called an open set. So, a topology is a subset of open set. It is more than a set, okay? It is a set with additional information. As you can see here, a topology is something we need to choose, okay? It's not automatically there. It is a choice. And whatever you make a choice, it provides a structure. Now that we have recalled what topology or a topology on a set is, we need to introduce now the morphism. So in today's lecture, we are going to talk about continuity of maps. First of all, let's talk about a map. And you know what a map is. In fact, a map is something called F, okay? And it goes from one set X to another set Y, as you can see here, where X is the domain and Y is the target set. If we picture or we represent the set X by its elements 1, 2, 3, 4, and we picture the set Y, or we represent the set Y by its elements A, B, C, D, you see that a map takes every point, okay, on the domain to some point on the target. For instance, 1 and 2 can be taken to B, 3 can be taken to D, and 4 can be taken to C. There is no need that every point on the target to be hit. For instance, A is not hit, but B has been hit twice, and there is notion for that. If there exists points like A, we say that a map is not surjective because some point on the domain, on the target, are not hit. If there exists points like B, we say that a map is not injective because certain points on the target have been hit by more than one. As you can see, a map, okay, is only define between two sets. You don't need no further structure on X and on Y to say that F is surjective, injective, or bijective. However, I give you this function F from X to Y, and I ask you if F is continuous. Does it make a germ? The answer to the above question of whether F is continuous depends by definition on which topologies are chosen, okay, on the domain X and on the target Y. So, in order to decide continuity of maps, you need to decide on some topology on X and on Y. Only then you can write down the useful definition of continuity of maps. From this, we have the following definition. Let X Tx, Y Ty be two topological spaces, where Ts is a topology on X and Ty is a topology on Y. A map F from X to Y is continuous with respect to Tx, is important, and Ty if the inverse image, okay, of all V in Ty lies in Ts. In other words, if the inverse image of all open sets in Y is open in X. Now, if you want to understand everything, you must understand this trivial example. So, let X be the set just consists of elements A and B, and Y be the set just consists also of elements A and B, and F defined as you can see in this picture. Question: is F continuous? In order to decide continuity of F, we have to choose some topology on X and on Y, okay? So, on X, I choose the discrete topology, Tx, as you can see here, and on Y, I choose the trivial topology, Ty. Now, the inverse image of the empty set is by definition the empty set, and it lies in Tx. The inverse image of the set with element AB gives X, and X lies in Tx. As you can see, the inverse image of all open sets, okay, in Ty lies in Tx. So F is continuous. This brings me to the end of this third lecture. Thank you very much. See you on next time. Please don't forget to subscribe to my YouTube channel. Bye bye.